So in this video, we're going to take a look at the practice chapter 4 section. So this section focuses on pedigrees. So here I have assigned you a packet of pedigrees to look at, and most of them are going to have you try to figure out what is the pattern of inheritance, as well as figure out the genotypes of various individuals. So just like the practice chapter 3, a lot of this I'm doing off the top of my head, so I don't have a prepared script or anything like that. So hopefully this will give you an idea of my thought process as to how I actually solve these problems, as opposed to me just reading off notes or something like that. Okay, so let's look at question 1. So the filled symbols are affected individuals, and you can assume that the disease allele is rare, and therefore individuals marrying to the family are unlikely to have the defective allele. Okay, so that's helpful. So as you know, males are going to be squares and females are going to be circles. So that should be familiar to you from your textbook reading. So let's clear this out since we're going to mark this up quite a bit. Okay, so looking at how this disease is inherited, it looks like in each generation, so generation is 1, 2, 3, and 4, it looks like it's present in all of those generations. So when you see a disease that's present in each generation, so here we have 4 generations of families, it's present in all of those. That's a pretty good sign that's going to be dominant. So right now that's just a hypothesis. So after we come to whether or not this is autosomal or sex-linked, then we'll go back and start doing genotypes and Punnett squares and whatnot to ensure that I made the correct hypothesis. Okay, so we believe it's dominant since it shows up in each generation. And if you look at the difference between, or if you look at the sex that are affected, it looks like it's pretty evenly distributed between males and females. So that's a pretty good sign this can be autosomal. If more males are affected, that's usually a good sign that it's going to be X-linked. But again, here we have 4 males affected, 3 females affected. So that's pretty much equal between the sexes. So we're saying this is autosomal dominant. Okay. So now let's start filling out genotypes assuming it's autosomal dominant. So if it is autosomal dominant, we shouldn't run into any issues trying to figure things out. Okay. So for all the white squares and circles, we know that's going to be recessive. So if they're recessive, they don't have the disease. So if they're homozygous recessive, I should say. Okay. So we've come up with a hypothesis as to the mode of inheritance. The second step is now to find the genotypes. And we're going to assume that it's still autosomal dominant until we can find a reason to disprove it otherwise. But right now this is our best hypothesis, so we're just going to go with that. Okay. So it looks like we're able to produce unaffected offspring from the crossing of an unaffected individual with an affected individual. So this means something like this white square right here has 2 lowercase a alleles. So that means they must have gotten 1 from their mother and at least 1 from their father. So that means the father must be heterozygous. There's no other possibility where you can get 2 recessive alleles. And knowing that, we can then fill out the genotypes of these individuals here. So we know all their offspring that are affected are going to be heterozygous. Again, the mother is always going to give one lowercase a allele or one recessive allele, so we know all of their offspring are going to have at least one recessive allele. Similar idea here. So we have we have homozygous recessive, so we know that all the offspring from that cross are going to be heterozygous if they're affected. So they must get at least one recessive allele from that mother. So then we cross these two right here. So again, that offspring is going to be heterozygous. This one we know since they're unaffected, they're going to be homozygous recessive. Okay, so I think this pretty much solves this pedigree. So there's nothing so far that looks out of place. If we would have chosen the wrong pattern of inheritance, we would have run into some issue with the genotypes at some point. So let's look at individual number 1. So we know since they're unaffected, they're lowercase a, so the homozygous recessive. Individual 3, also unaffected. Individual 4, so we know that we have an unaffected parent, so they must have at least one recessive allele. But they are affected, so they must have one uppercase allele. So uppercase a, lowercase a, and number 5, they're unaffected, so lowercase a, lowercase a. So a pretty straightforward pedigree, not too challenging. For part 3, that's pretty straightforward. All you have to do is make a Punnett square there, crossing individuals 2 and 3. So we know what their genotypes are, so you just cross those and make a Punnett square. Okay, so part B of question 1. So again, this disease shows up in each generation. Here, it looks like it might be skewed towards females, but we do have an affected male. So for this, I would probably say it's going to be autosomal dominant. If it was all female or all males, then it would be maybe a different pattern of inheritance. But here, since it's such a small pedigree, and since there's at least one male affected, I'm going to say this is autosomal dominant. So right now, that's my hypothesis until proven otherwise. Okay, so that leaves us with the same known information as before. So those are going to be lowercase a, lowercase a, lowercase a, lowercase a. Again, we have one parent, homozygous recessive, so there must be at least one lowercase a allele, one uppercase allele for 6. Okay, and that means for 7, we get unaffected individuals. So that means 7 must also have a recessive allele as well. So here we have AA. So one comes from the mother, one comes from the father. So we know their genotypes there. Okay, so it looks like we're finding the individuals 6, 7, and 8, and we're looking for their genotypes. So 6 we already know they're heterozygous. 7 we know they're heterozygous. And then 8. We know that since they're unaffected, they must be homozygous recessive. So again, we didn't run any issues assigning genotypes. So it looks like this is autosomal dominant. So we're just going to cross 6 and 7 to part 3. So that's just going to be heterozygous, heterozygous, and simple cross. And you can fill it out and figure out what the probability is there. And so in question 2, it gets a little more tricky. So it looks like we have this asterisk mark right there. So that means this individual right here is not carrying that allele at all. And it also looks like they're unaffected as well. Okay. So now this is a little bit different from the other pedigrees we saw. So in the other pedigrees we saw that all generations were affected. So generation 1, 2, and 3 in this pedigree were affected. And generations 1, 2, 3, and 4 were affected as well. Here though, it looks like we can skip a generation. So if you can skip a generation, that usually means it's recessive. Also, if you notice, it's only affecting males in this case. So in part B, we had both males and females affected, although females was a little bit more skewed. And for part A, we had both males and females affected. But here, though, we just have males affected. So this is probably going to be X-linked. And remember, males are more affected by X-linked diseases because they only have one X chromosome. So remember, males are XY, so they're going to have some sort of allele on their X chromosome. So they don't have sort of a backup like females do, since females have 2 X chromosomes. Okay. So let's start figuring out what we know. So we're saying it's X-linked recessive. So that tells us something about the males in this pedigree. So any male that's unaffected is going to have the dominant allele. Any male that is affected is going to have the recessive allele. Okay. And so we were able to produce males with a dominant allele. So we know this female mother has at least one dominant allele there. We know that the father always has to give the females this recessive allele. So for something like this female right here, we know she has to be heterozygous. She's unaffected, but we know she has to get at least one of those alleles from her father. Okay. Same thing with this female right here. We know she's going to be heterozygous. And let's see what genotypes we need to find. So we need to find 1 and 3. So for 3, it's pretty straightforward. We already figured that out. So it is heterozygous. For 1, it's a little bit more tricky. So for that, I would do 2 Punnett squares. So let's put the father at the top and the mother at the side. So we're going to do 2 Punnett squares. One assuming she's homozygous dominant, and another assuming she is heterozygous. And we're going to see what the offspring would look like for that. Okay, so it looks like for this one right here, 0% of the offspring are affected. For this one right here, it'd be 50% female, 50% males that are affected. So looking at the generation 2 here, nobody's affected. At least none of their children are affected. So it seems like this is a much more plausible genotype here, specifically this female genotype right there. So it looks like she's going to be homozygous dominant. Okay. So now it's asking you about A and B. So we know the genotype of this parent right here. Let's figure out the genotype of this female right there. So this female is going to be weird. So this asterisk right here. For exam questions, I won't ever give you an asterisk like that where somebody loses an allele. But here we have a female. She has X and nothing there, and then she has X. Uppercase, I believe. Let me double check that. Yes, so I think in this case, if she had the lowercase allele, then she would have the disease. So if she had the recessive allele, she would have the disease there. So let's do this cross. Okay. So A is going to be a female, so we're going to look at the females. So it looks like there is a 50% chance of her being affected. So here in this question doesn't make it quite clear how to deal with this allele that's missing for one of the X's. But I'm guessing if they have no allele on one of their X's and recessive allele on their other X, then they're going to have a disease. If they had a dominant allele on the other X, then that would protect them. But here they don't have that, so you just have the recessive allele, and that makes them have a disease. So that would be 50%. What's the probability of being affected? So B is a male, so it looks like is 0%. So even though this male is missing the allele, it looks like for this asterisk male right here, even though he's missing allele, he's still fine. So I'm guessing if this XY male that's missing the allele doesn't have it, then he's going to be okay. But again, it's not quite clear from the question. Okay, question 3. So here again we have skipping of generations. So again, a very good sign that we're looking at a recessive disease. And it affects both males and females. So we're going to assume it's going to be autosomal. Again, until proven otherwise, if you chose this wrong, if you choose it incorrectly, it's probably going to be very obvious once you start assigning genotypes that something is haywire there. Okay. So it's autosomal recessive, so there isn't a lot we can say about this pedigree so far. So we know these people have to have true lowercase alleles, and we know that these parents have to be carriers. So we know they get one from their dad and then another recessive allele from their mother. The reason why I know they have at least one dominant allele is because they're unaffected by the disease. Okay, So we're going to say they're heterozygous. Here, it looks like none of the offspring are affected by the disease. So this is more in line with this female here being homozygous dominant. If she was heterozygous, we would expect half of her offspring to be affected by the disease there. So that does not match what her offspring are. So she is more likely to be dominant or homozygous dominant. Okay, so we can cross that off. So she's homozygous dominant. We can do the cross there. Essentially, all the offspring are going to be heterozygous. So that's heterozygous, zygous, heterozygous. Okay. And then that's essentially as far as you can go. So for this question, they actually put all possible genotypes. So there's going to be some information that we just can't determine from this pedigree. So the genotypes of individuals 1 and 2, we can't be quite sure what they are based on this disease being autosomal recessive. So this person here could be homozygous dominant, or they could be heterozygous. Same with this person here. So for all possible genotypes, it could be heterozygous dominant or heterozygous. For individual 4, though, we're fairly certain it's going to be heterozygous. So again, be careful with the tables, make sure to read them. So this one says all possible genotypes. Let's go back to other tables and see what they said. So this one just says genotypes. So this one implies that you will be 100% certain what the genotype is. Same with that one, and same with this one. So really it was until question 3, part B, that we saw all possible genotypes instead of just genotypes. So just be aware there's some wiggle room with some of these genotypes. Okay. So it looks like we have part T now. So here, let's look at this. So it skips a generation, so it looks like it's recessive. And it looks like it's much more frequent in the males than the females. So that makes me believe this may be X-linked. So we'll go through and assign genotypes and see if we run into any issues with that. Okay, so assuming it's X-linked recessive, we know quite a bit now. Male is that. Female is going to be this. It's going to be that. That male's going to be that. So again, we have the asterisks here. So nothing that will show up on the exam, but here is in the packet. So these individuals don't have any alleles that contribute to this disease. Okay, we got another affected male there. So for this female here, we can then figure that out. So we know that she has at least one uppercase A allele since she is not affected. But she does have an affected male, so that means she must have one recessive allele as well. So she is heterozygous. Whoops. So really we can stop there, since it didn't ask us to find genotypes, so we don't have to fill all this out. But here we're going to be crossing individual 3 from the first pedigree. So it looks like this one. So they're lowercase a, lowercase a. And it looks like they're not going to be affected by this gray allele. So if that's the case, we know they're XB. Here we're going to switch from A to B just to make it clear. And they have Y. So they're affected by the black disease, but they're not affected by the gray disease. So that's the genotype of that parent right there. And we're looking at individual 6. We're saying this is X-linked recessive. So we know they're X lowercase a, X lowercase a. And we're going to say they're not affected by the black disease. And let's see if it gives any hints. So it doesn't say anything about that. So we're not quite sure what the second allele is going to be there. So it's kind of ambiguous. So with the genotype, there's son for the 2 disease genes. So for the son, we know he's going to get, whoops, switch this to B's. He's going to get 1X from his mother, and then a Y. So he's going to have the disease. So he's going to have the gray disease. And then we know he's at least going to get 1 recessive allele from his father for the black disease. So again, we're not quite sure what's going on with the mother there. Okay, so let's look at the genotype of the daughter. So we know we get 1 lowercase b allele from the mother, absolutely, and then we get another lowercase b from the dad. And again, we still can't be quite sure about the A allele. So it really depends on what the mother is there. So this is not clear from this question. So hopefully all that gave you a good idea of how to do pedigrees. So I definitely highly recommend you do more than just the ones I've given you here. In regards to exam level questions, it's probably going to be more along the lines of questions 1 and 2, so about the first page and a half. After that, it starts getting a little bit trickier, so we don't go that advanced. But I think it definitely is good practice. So definitely do more questions, pedigree questions, and there are a lot of them on the internet, so do search around, and you'll be able to find more to do.